Hello everyone, I'm very happy to share my work on surface-based representation of 3D shapes. This is joint work between ENPC with Theo Deprel and Mathieu Aubry and Adobe Research with Brian Russell, Matthew Fisher and Voveke. There are several ways to represent 3D shapes, which is the motivation for this workshop. In this talk, I discuss a 3D representation based on surfaces. A surface representation can be used without post-processing to do rendering, to compute surface interactions, to penalize surface interpenetration, and as we'll see in the talk, to compute shape correspondences. Our key idea is a new parameterization of 3D surfaces based on deformations. We parameterize a target 3D surface by the deformation from a template surface to the target surface. Of course, this requires a template, and we're going to discuss several cases. The first case, which is the simplest one, is shape categories with a clear shape template, such as human body scans. We'll discuss later harder categories which do not have a clear template. Let's see now how we can parameterize these surfaces in practice. We propose to model the surface deformation by a multi-layered perceptron, an MLP. This MLP is supposed to deform a common template into a target surface, so it should be conditioned to do that on the target shape and the template. More precisely, we condition the MLP on the target shape embedding, obtained by a shape encoder such as PointNet, and a 3D surface point on the template, such that the MLP, given the target shape embedding, acts as an R3 to R3 function, taking a point on the template and outputting a 3D point on the reconstructed shape. This R3 to R3 function is run in parallel on all the template points, which results in a reconstructed shape with the same number of points as the template. Since the MLP deforms each template points independently, this means that there is a 1-1 correspondence between template points and its deformed version. We say that the reconstruction is thus in dense correspondence with the template, and visualize this with colors. An important aspect of the method is that the MLP is conditioned on the embedding so that each transformation is specific to the current sample. In fact, the key novelty here is to use MLPs as a family of parametric and continuous functions, and just use the embedding to predict which specific instance in that family we want to use for the current sample. These MLPs are trained on a large shape collection, and there are two cases. Either we have correspondence annotation in the dataset, and we can use these MLPs with a fully supervised L2 loss, or we don't, and we use an unsupervised reconstruction loss like the chamfer's distance, and we couple it with regularization losses that penalize distortion of the surface. Since our method has a fully unsupervised setting, regardless of how we train the MLP on the collection, we can always refine the learned deformation by a test time optimization on the new test sample using our unsupervised losses. The variable that we optimize here is the embedding of the test sample, and we initialize the optimization by the learned embedding. After optimizing the embedding, the quality of the reconstruction have improved. If the initial reconstruction is good enough, this test time optimization doesn't change much. However, it is critical if the initial reconstruction has clear artifacts, as you can see here on the arms. This reconstruction approach by surface deformation is robust to noise, holes, partial scan, and generalized to difficult poses and shapes. And because all the reconstructed shapes are by design in dense correspondences with the template, which we visualized with colors previously, it leads to a simple algorithm for shape matching, and we called it 3D coded. And this algorithm achieved the state-of-the-art in the Shrek 19 competition and a dataset of human scans called FAUST. We've seen how to deform surfaces for categories that have a clear template. but most categories don't have neither templates nor correspondence annotation. We now discuss two options to deal with those harder cases, like the chair category. In the absence of template and correspondence annotation, a first approach is to learn to deform any shape into any other, which can be achieved by conditioning the deformation MLP on both the target and the source surface. We propose to use cycle consistency constraints to encourage those deformations to respect shape correspondences. Indeed, for any pair of shapes, the deformation of a shape A into another shape B should be the exact inverse of the deformation from a shape B into the shape A. Similarly, for any triplets that you can see here, if you compose deformation along a cycle from shape A to B to C and C to A, it should lead to the identity function of R3. Since we don't have access to a template, a key aspect of this approach is to design a selection criterion that tells you, given a new test sample, which training shape you should use as the source surface. Another approach to handle categories without templates is to deform a universal template, such as a sphere or planar patches. This approach is called AtlasNet. Our experiments with human body scans show that deforming a template specialized for the category leads to better reconstruction results than using universal templates. So for categories without clear shape templates, we thus propose to learn the template, which we call learning optimal elementary structure. To learn these optimal elementary structures, similarly to what we did before, we start from handcrafted templates as initialization, planar patches here. But this time, we make the points of the template learnable parameters of the model. And during training, we backpropagate gradients all the way to the spatial position of those template points. So after training, the templates have been specialized in order to best reconstruct the training data. Hence, in the best cases, we can see semantic parts appearing, like plane tails or reactor here for the plane category, without any kind of annotation on parts. It's just simply done by minimizing an unsupervised reconstruction objective. So beyond interpretable results, learning parts also gives a clear boost for reconstruction and correspondence. It is time to wrap up. We have seen how to parameterize the surface of 3D shapes with neural networks by their deformation from a template surface. And we have shown the strengths of this approach in several applications doing analysis by synthesis. In particular, we showed that surface deformations could be used for shape matching to learn parts, and just recently to do clustering, which is work on Archive. Check it out. Thanks a lot.